Hello, good afternoon, everybody, and welcome to this MB's webinar about statistical engineering. Uh, our speaker today is Geoff Vining, professor of Virginia Tech, and well, most of you know him from our MB's meetings, and he's also the driving or one of the driving forces behind ICEA, the International Statistical Engineering Association. And as you see on your screen, he would be talking about statistical engineering. What is it and why is it important? And with that, I guess that welcome, Geoff, and the floor is yours.
Thank you, Xavier. It's a pleasure to be able to do this. This is my first webinar. God created graduate students for a reason. Usually they take care of the technology for me. It'll be a miracle if I can pull this off. So far, so good. Here's the basic outline of what I want to do today. I want to talk about the big picture on statistical engineering. The real foundation, statistical engineering is about solving complex problems. And the real underlying theory that's going to be driving statistical engineering is going to be basically just scientific method. So scientific method combined with systems and statistical thinking. And I want to make sure that we appreciate that kind of big picture on this. Um, that's about the point where I'm going to take a break and allow for questions. From there, I want to talk about the phases to a statistical engineering project and some of the basic concepts for how we approach the phases. What do we do within the phases? We often talk about core processes and overarching competencies. These are closely related to chemical engineering concepts of unit operations. And then at the end, I want to just kind of summarize, but what is statistical engineering's enduring value, which is why we should be doing statistical engineering. So the big picture, value to organizations is being able to solve complex problems. Usually they're unstructured. Xavier really hit it on the head in some conversations with me and Roger Hurl. He said they're a mess. And how do you begin to unwind the mess? Um, Often these complex problems are large. They don't have to be. They can still be complex and relatively small, but they all are going to require data in the long term for their proper solution. So the secrets to success, you got to have the right subject matter expertise for that specific problem. One of the concerns that I've seen in the past, particularly with statisticians trying to work on complex problems, they don't always fully appreciate the need for the subject matter expertise, particularly with the academics. They have a tendency to want to solve problems from their offices and not get engaged with the real problem. So that's why I really want to emphasize that subject matter expertise is essential. It's a team. It involves collaboration. And part of that subject matter expertise is how do you handle data? How do you properly collect the data? How do you properly analyze it? How do you properly interpret it? But it's not in a vacuum. So there's tool sets that are critical for success in solving complex problems, and it's a broad set of tools. And then what does statistical engineering bring to the table? It's a strategic and tactical deployment of the tool sets. And this, oh crap, there we go. I've tried to draw up a simple schematic to emphasize how all of this is connected. So at the top, I'm emphasizing, we've got the people aspect. So we have to have the true subject matter experts from the critical disciplines. We got to build teams and we got to lead to collaboration. People skills are absolutely essential for success. But then we also have to have the right tool sets. So the tool sets beyond, above and beyond the subject matter expertise. I mean, that's absolutely critical. But the other set of tools to complement the subject matter expertise, there's statistics, data science, business analytics, all of the stuff that's been done, you see commonly in the statistics journals. We talk about it a lot within NBIS. We also have industrial and systems engineering, operations research, management science. I'm engaged in trying to get up a Virginia Tech Center for Statistical Engineering, and it's joint with industrial engineering and statistics. And I'm learning a lot about their tools and how they should be an important component in the tool sets for solving complex problems. And then finally, here, the organizational behavioral psychology. It's critical for the basic tool sets in organizational and behavioral psychology to bring out the best in the people. And too often we don't emphasize that. I mean, how many of us in graduate school had any kind of meaningful course material on organizational behavioral psychology? So again, it's the combination of the right people, getting them to work well together with the right tool sets. And then the whole idea of statistical engineering is to provide the strategy and the tactics for integrating all of that to come up with efficient and effective, better solutions to complex problems. Statistical engineering is about how we can learn from previous complex problems to come up with better solution pathways for the next problem. So the basic foundations of the statistical engineering strategy, scientific method, systems thinking. It's one reason why ICEA is very focused on learning from chemical engineering. My original training was chemical engineering, so they are very much trained from the very beginning in systems thinking and scientific method. Structured but not a rigid approach. One of the major criticisms of Six Sigma is that it's so rigid that it eliminates the opportunity to do innovative approaches. The idea here is to provide strategy and suggestions for how to deploy, which would be the tactics. It's structured, but it's a journey. So it's the notion of you adapt and overcome, and as a result, then you learn from the journey, which then becomes fundamental for how we revise how we should put the tools together for the next attempt to solve a complex problem. So this is an iterative procedure. Those of you who know me well, I'm very much into iterative learning. That's the whole basic foundation for the theory of statistical engineering. To make sure we understand scientific method, it is a sequential learning strategy, much like what we're trying to talk about within statistical engineering. Crucial to it is you got to understand the actual problem at hand, which often is not the problem that you are handed to by leadership in your organization. They may understand it in one sense, but they don't really have the core of what the real problem is. So that's the first step. You define the problem as you understand the real problem. You discover solutions. You're moving between the concrete and the abstract. Back when I was taught scientific method, abstraction was basic mathematical models, often based on differential equations. Now we've got the basic code in the background, deterministic code that is based off first principles. It's what I was taught in the 70s on steroids. But we take advantage of that kind of approach, taking advantage of the computing, particularly these deterministic models, as they get tweaked in terms of real data. From there, you develop a theory for the specific problem. You test the theory using data, and you modify as necessary. It's an iterative procedure. And critical to it for any interesting, complex problem is the interdisciplinary collaboration. I just heard in the past week a new buzzword in the US for research, transdisciplinary research. Well, statistical engineering is transdisciplinary. Data are the keys to successful application. We got to have the proper data collected. We've got to clean it correctly. We got to make sure it's relevant. We have to do the proper data analysis. We have to do the proper data interpretation. It sounds a whole lot like what we do in statistics and quality engineering and data science and analytics, and it's true. Don Marquardt, who was in charge of the statisticians at DuPont for many, many years, when he gave his presidential address to the American Statistical Association, called it statistics the handmaiden to the scientific method. It's essential to support the scientific method, but it's not the scientific method itself. The subject matter insights have to guide everything. The data analysis flows from that. And then ultimately, all solutions require subject matter validation and verification. That's why the subject matter expert is so critical to the proper solutions for complex problems. But it's the entire team, it's the entire collaborative effort that is essential to do this efficiently and effectively. A systems approach is fundamental to this because we're dealing with a complex problem. And there are going to be stages, there are going to be phases to the solution pathway, to the journey. And it's fundamental, it's very important to think in terms of this as a system. Usually the problem itself is a system and consists of stages. So a review of the notion of statistical thinking that all work occurs within a process, that there's variability within each step of a process, and that the key to improving quality is to reduce variability. And it's systems thinking. Now, we've been talking about statistical thinking for over 20 years, but I think an important missing element, we haven't had a systems approach to the solution itself. And that's what we're trying to provide here in statistical engineering. That's the reason why I want to emphasize it's strategic at the highest levels. Should we deploy? What resources do we need to deploy? What people do we need to deploy? And then how do we deploy them, which becomes more tactical. The model's been for us has been chemical engineering. The origins of that was origins of chemical industry is Germany, but the origins of chemical engineering is the US. And the reason was in Germany, everything was being driven by specialty chemicals. Chemists worked directly with mechanical engineers. There was a large profit margin. There was no attempt to make it large-scale production. In the United States, the chemical industry was dominated by commodities, very large-scale production. So economy of scale, learning how to be more efficient with the process became fundamental. So the engineering was really on how to make the process, the system, more efficient and effective. So we see that as an excellent paradigm for how to implement statistical engineering. Solution strategies have to take this kind of systems approach. I like to summarize the strategy for success as we need the right tool at the right job at the right time, correctly applied. And the key then is you got to know your tools. You got to know what jobs they are appropriate. You need to recognize at what time in the solution process you need them, and then you got to make sure you correctly apply them. Too often, like in Six Sigma, we relied so much on the training of the engineers, that they often didn't correctly apply the tools. In some cases, they did wonderfully well with very simple tools. In some cases, they had problems with more complex tools. The notion of correctly applied goes back to the heart of why we need the statisticians, the data scientists, the business analytics people, the OR management science people to make sure that the tools are being correctly applied. So sustainable solutions are very, very important. That's the key to what we're trying to develop here. And I want to make sure that the tools are not confused with solutions. And too often that's what you see. And I see that too much in the statistics and quality engineering literature. The tool that's proposed as a solution, no, it's not. It's a mechanism to the solution. So once again, this is that schematic diagram of statistical engineering. I want to just keep emphasizing it's a combination of getting the right people, especially having the true subject matter experts fully engaged and as full partners, both with themselves, with the other disciplines, and with the statisticians, the analysts. So again, the people component, absolutely critical. The right tool sets, and I'm viewing the tool sets down here at the bottom as the handmaiden to the scientific method, with the scientific method being more owned by the subject matter experts. So I think this is a good point for questions. Xavier, I'll turn it over to you.
Some question coming on. System theory has many meanings. What is your definition of a system?
That's a good question because I'm not a real expert in systems theory. I'm going to come at this from my chemical engineering background and from my experience in working with complex processes. Uh, for me, a system is any process that has stages to it that are interconnected. So there are several levels of system thinking from my perspective within statistical engineering. If we're dealing, let me go to my own personal experience. Let me take an example of a complex problem from a chemical process. Well, first off, the process itself is a system. So I know that any approach to a solution for that problem has to respect the actual nature of the system that is the process. I have discovered that an amazingly effective tool, and it comes back to systems thinking, is just the flow chart. You know, how many problems have we dealt with as a profession where people didn't even know what their system was, what their process was, and that in creating a flow chart, suddenly all of the problems come out, and you begin to see the inefficiencies. So that's one level where I think about systems. But I also think about systems and how we apply the tools. So I would argue that my paradigm, the right tool at the right time, the right tool for the right job at the right time, correctly applied, does reflect systems thinking. It's a structured approach, a series of phases for how you would approach the problem. So I hope you're getting some idea of how I'm seeing systems thought. I do know there's a whole discipline on like systems engineering and systems theory. We have not gotten that detailed in it in our own particular efforts, but perhaps that is something that as we create the discipline of statistical engineering, we need to explore more. Just as I'm learning that operations research and management science ideas were underrepresented in our first thoughts of the discipline, perhaps this systems thinking is something that we need to also look more into.
Geoff, uh, there are some other questions about system thinking, but I think that this has already been done. But there is an interesting question saying if you can uh, tell some examples where statistical engineering has succeeded, where traditional statistics methods have failed. So,
Roger Hurl has a great example from when he was at General Electric. They were dealing with the defaults of portfolios. If I remember right, it was in bonds. And they were able to, in a year, take a very poorly defined problem, one where they really didn't know if they could come up with any kind of solution, even the senior management, that a solution from the theory of economics, from the theory of an efficient market, should not be able to be done. But no market is completely efficient. And they were able to come up with a solution that was going to save several $100 million per year for General Electric. I would argue that some aspects of the F-35, the Joint Strike Fighter in the U.S., has been an extremely complex problem. But again, there have been examples of applications of statistical engineering to those kind of specific subsystems, and with great success. William Brenneman last year at NBIS gave a very nice statistical engineering example from Procter and Gamble. So yes, we have case studies out there. We're trying to compile and put them up on the ICO website. But the more success stories that we can compile and distribute, I think the better people can begin to see the inherent value of what we're trying to do.
uh, another question is whether you can organize the tools in different levels of abstractions uh, and how this relates or what is if the problem solving strategy of Six Sigma is this DMAIC is different from the problem-solving strategy of statistical engineering? Or
I'll take the last one first. I mean, I would view DMAIC as just an application of scientific method. In fact, my first thoughts of what would be a theory of statistical engineering started from the DMAIC process. Um, define, measure, analyze, improve, control is a variation of the Deming-Schuhart plan, do, check, act cycle. And other people have written that that really is basically a formal mechanism for implementing the scientific method. Now, I would argue that the scientific method is more flexible than the DMAIC. So I view the DMAIC as an example of an application of the scientific method. Now, I also heard, are there different levels of abstractions, different levels of use for the tools? Clearly there are. Clearly there are. And, it's part of the art and science of solving these problems. It's part of why it's so important to understand our tools, to understand their limitations, to learn how to modify them as appropriate, and also learn what's appropriate for the context. You know, I would argue that planning an experiment is a fundamental concept for improving processes. But, in some cases, a simple 2 to the k factorial is going to be extremely valuable and understood by the people having to implement the solution, as opposed to an extremely complex and sophisticated split, split, split plot. But there are occasions where we need that level of sophistication. The key is to understand at what level of the abstraction, at what level of the application do we need the tool. That's why I keep trying to emphasize it's the right tool for the right job at the right time, correctly applied. And frankly, the simpler the tool, the better. But we've got these much more complex tools in our toolkits for a reason. We need them sometimes.
okay, I think that we can better go on now, and at the end we'll have another chance for questions.
Okay.
Okay.
So the phases of statistical engineering. The first is you got to identify the problem. And that's not a simple task. Generally, you get the problem from a senior leader in the organization, and they may just understand it as we're losing sales because this product isn't attractive to our customers. Okay, lovely. Oh, you've just told me something pretty obvious. It's not attractive to the customer. We're losing sales. So, but in order to solve that problem, we've got to identify what is the specific nature of the problem. Generally, there's more than one problem. So the first step is, given a task from a senior leader, identify what is the true nature of the problem, and in fact, you may want to break it up into a system, a series of problems. Once you have the problem, you need to provide the proper structure. What is the content? What is the full nature of that problem? For example, we may have, I'll go back to my own experience. We're dealing with pencil lead, and we're discovering that the pencil lead is, is too scratchy, and it's turning customers off. Now, there are multiple causes for that. So part of what I have to do is to provide the right structure. So I've got to go back into the ceramic engineering process and look very carefully. What would be the fundamental nature of the problem with the thing being too scratchy, sounding harsh? And so that's the notion of providing some structure. Now, I did that in a very simple context just for this conversation. Clearly, the more complex the problem, the more complex the structure, and the more time the team needs to look at what is that fundamental structure. I'll give another example. Again, it's relatively simple. I'm dealing with a NASA project where we're looking at the expected life of carbon overwrap pressure vessels. So these are under extreme pressure. And what is the actual mechanism for failure is open. It's pretty much a black box. So how to approach being able to predict the expected life under use conditions for a carbon overwrap pressure vessel in a spacecraft We had to provide a kind of bit of structure and a lot of debate about what was the nature of the basic mechanisms. It's important then to understand the full context, particularly the more complex the problem. Ron Snee likes to talk about a problem he dealt with in DuPont, where they were losing sales for one of their grades of nylon. They had been the dominant leader in the market. They were down to fourth in the market. They had very fundamental quality production problems across, I think, 8 facilities on 3 different continents. So it was fundamental for him to understand the science, the business, the personnel, and all the politics. And that actually can have an impact then on what is the structure of the problem or how you will approach the problem. Notice these first 3, none of them are statistical. You want to know the truth. Then we start developing the solution strategy. So this is where we've identified the problem. We've got a good structure for it. We understand some of the constraints due to the context. So now this is where we start combining the subject matter expertise with the appropriate data collection, data analytic tools, the basic data interpretation. So we're developing the solution strategy. How do we approach this? What is the order we attack these problems? Understanding that as we attack problems in series or in parallel, that we'll be learning from that. As we develop a solution strategy, then we move to how we develop and execute the tactics. This is an iterative process. 4 and 5, you iterate as necessary. As you execute the tactics, you learn. That's going to modify your solution strategy. Ultimately, you feel like you've come to a reasonable final solution. So you determine that it's sustainable and you deploy it. One of the key notions about that iterative procedure, we need to learn from innovation. In innovation, failures are actual successes. They're opportunities to learn. Failures are important. The issue is to learn from the failure. So failing early on a proposed approach to the solution is not a bad thing. Just learn from it. That's a secret of innovation. So failures are important, but what you do is you learn from them and move on. Adapt and overcome is an appropriate motto. You investigate the failures very, very thoroughly. And as a result, then you have a very nice case study at the end. The idea is to learn and to document. This is very much an iterative procedure. And sometimes I think we lose sight of that. After the project, and again, we've already had some questions like this. Wouldn't it be wonderful for us to be able to see case studies, that document the success of statistical engineering? I argue that every statistical engineering project, every solution to a complex problem needs to be well documented. That documentation may be considered proprietary. I'm okay with that. That becomes learning for the next project within that organization. Personally, I would like to see it open to the public, at least redacted to the point where we're not giving away proprietary information. But I think that the proper way to close any of these complex solution processes is with a real case study to document the learning. And by that I mean what worked well, what didn't, and what are the recommendations for next time. And so when I say publish the final document, it could be publish it in a journal like Quality Engineering, Journal Quality Technology, could be published in a place like Quality Progress, it could be in a subject matter journal, or it could just be in the archives of the organization. But the key is don't throw away that learning. And the more we can share it broadly, the more we as a community, as a discipline, can learn more efficient and more effective ways to build our solutions. We've got to stop thinking about solutions to complex problems as one-off. What are the learning opportunities so that the next time we run into this problem, we can be efficient and effective in its solution? The core processes, what I would call the critical bodies of tools, data acquisition, and this is in all senses of this, particularly in Industry 4.0, when we're dealing more and more with sensor technology, all sorts of new issues in data acquisition. So this is much broader than planning and experiment. This is any way that we're collecting our data. Once we have data, the initial data exploration, more and more visual tools are being developed, particularly for analytics. Modeling is crucial. Personally, I'm a small data person, but so the traditional statistical methodologies are important in modeling, but I also recognize a huge contribution from modern analytics, from big data. I'm beginning to appreciate much better deep learning and neural nets, which in the past I never took the time to really fully appreciate, but they can be very, very effective modeling tools. From there, it's the inference to the process and the problem, and I'm not talking about inference in the sense of mathematical statistics. We're talking about what did we learn about that process or that problem. So I'm less worried about uniformly most powerful test. I'm more interested in what in the world did we learn about from this experiment, from this exercise, about how to improve this process or problem. So it's going back to the final conclusions about what we did in the process. The next core process is learning how to evaluate and trial deployment of tentative solutions. Because the goal isn't to come up with a solution, the goal is to come up with one that is sustainable. So we don't have a solution until we actually have gotten to the point. I don't know what this is asking for. Okay. We don't have a final solution until we've gone through appropriate evaluation. Once we've determined we have one, then we got to go through all the processes to ensure that we can sustain that result. The second law of thermodynamics always applies. Solutions will always degrade, so there need to be mechanisms to monitor the solution. I think very much along the lines of Duran with breakthrough and control. I see this deployment of the final sustainable solution very much in his sense of control and quality management. There we go. Overarching competencies, these are not what we would correspond to what would be the unit operations in chemical engineering. These cross all of those basic core competencies, things like data visualization, optimization, project management, teamwork, organizational culture. So clearly the people aspect is extremely important. That's the teamwork and organizational culture. We're managing a complex project. It's a system, so being able to understand that properly. Visualizing data pops up all the time in these processes. And this is where I'm really learning a lot from the industrial engineering operations research people. Optimization is crossing everything. These solutions are a journey. And what we're trying to do within statistical engineering is to come up with a well-defined roadmap. And there is one. We've got a general strategy. Now, you have to adapt it for your specific problem. As a result, each journey is unique. But we know what the factors are for success. You got to have the proper teamwork and collaboration. You got to have the proper blend of skills. You got to have people who understand and appreciate the other skill sets in the team. You have to have a proper understanding of all the tools and their roles, both from the subject matter expert side and on the data analytics sides. You got to understand how to deploy the tools strategically. And, success often comes back to the quality of the leadership. The stronger the leadership, the wiser the leadership, the more likely you have success. So what is the enduring value of statistical engineering? I've ever since I've been in the profession since 1988. That's my PhD is 1988. And I have heard statisticians complain we don't get respect. Well, in an organization, you get respect if you deliver value. I had a conversation with Craig Barrett when he was the CEO of Intel. And I was talking to him specifically about the glass ceiling for statisticians. And there was a clear glass ceiling at Intel for the statisticians. And I got him to think about it. But what he ultimately said is the people who are going to rise up the technical leadership ladder or even the management ladder are the stars. These are the people who have demonstrated huge value to the company. So if you want respect in your organization, you got to deliver value. And, complex problems are great value to your organization. So to the extent then that we can morph what we do as industrial statisticians, as quality engineers, and make ourselves more valuable in solving these complex problems, the better we will be. And we see statistical engineering as a very important uh, approach to increasing the value of what we do. And again, we view it not so much as it's a part of statistics or data analytics, we see it overarching all of that. It's blending together what we do well on the analytics side with the subject matter experts. So the future state, the key is we need to learn how to use the tools most effectively to solve complex problems. So, and again, I'd like to end with, leadership at all levels, technical and managerial, are essential for us to have success. The future is a journey, and I want us to appreciate that. And one last bit, we do have the new professional society, ICEA. The focus is the emerging discipline of statistical engineering. I certainly invite all of you to join us in this effort. Our business model is based on NBIS. We're trying to do as much as we can web-based. Individual memberships are free. We have paid organizational memberships, and we're actually have money right now. It's kind of a miracle. And here's our website. So please feel free to check us out. We'd love for you to join us. So with that, Xavier, I have got maybe 6 minutes for a few more questions.
Yes, thank you, Geoff. I have one is related with what are the main topics behind or besides the idea of what is the right tool, the right job at the right time, and so on. What are the main that the people asking the question understood that was one of the topics of statistical engineering research? What are the other main topics and ideas for research related to statistical engineering?
That's a great question. That is an absolutely great question. I think we as a group are beginning to really try to define what are those areas for research. So I'm encountering that. So I'm not trying to dodge the question. I don't have a good answer at this point. But I'm seeing the process as I'm developing this Virginia Tech Center for Statistical Engineering, because we have a very, very good industrial engineering program here at Virginia Tech. And they're dealing with a lot of industry 4.0 problems, a lot of them. So I'm really enjoying learning from them the nature of the problems they're working on. And I think it's going to be more experience with these complex problems that will help us refine what are the specific research areas we need to pursue. So I'm learning a huge amount this particular semester, working with my colleagues in industrial engineering to help shape my own thoughts about what the research areas are. We have not gotten to that point in our conversations, but we are going to get to that point in a week or in a month or so. And we are developing a white paper. And there are two specific objectives of the white paper. One would be research areas for statistical engineering, and the other is curricular development, pedagogy. And it is my intent for us to publish the white paper for the Virginia Tech Center for Statistical Engineering on the ICEA website. So I'm not giving you a great answer now, but I hope that you'll follow us on the website. And when we get that white paper up, that will help give you a better sense. I also hope it will inspire other groups to write white papers on what they see as the right research topics, especially those from organizations outside of academia. So again, I apologize I can't give you more specific examples, but it's a journey that we have to take, and we are beginning to do that. And I'd like to get more groups engaged in that activity.
Okay. One quick question maybe before is where the faces come from? Are they related with this research, or is
These phases are out of experience. So it's building off mostly of Roger Hurl and Ron Snee's experience using Six Sigma. So what they're doing is extrapolating beyond what they have done within Six Sigma. Six Sigma will certainly fit within this context, but it reflects their learning about a general strategy for coming up with solutions. So it's experiential. This is not based on any mathematical theory, and it's our starting point. And again, with any kind of experiential theory, it's going to be subject to modification over time. But we as a group feel like this is a very good starting point for how to uh, define the strategy of statistical engineering. So I hope that makes sense.
Okay, yes. Thank you, Jeff. There are still some other interesting questions, but really, we are scheduled to finish at a quarter to four. Uh, I just want you to just to remind you about this statistical engineering, covering this in detail at the spring meeting and this spring meeting. The conference is structured to have a lot of time for sharing and questions and answers and making our mind on what it means and how we can contribute to statistical engineering. So
I hope
that's
we get a bunch of the questions from today that I couldn't address or did not address well. And I hope they will. These are people who will come to the conference and we can engage in dialogue and conversation.
sure. That would be very good. I also think that we will have fun. Mid-June in Barcelona is a nice time to be here. So we'll try also to develop some activities to have fun together. It's 15:45, so I guess that it's time to finish. But if you gents can go on for 5 minutes, maybe we can stay. Some of us we can stay for a bit longer.
I can leave this open for some time now. Yeah.
Okay. So then maybe Jeff, a nice question for those that want to continue is this question relating about uh, the idea that we are in the age of data science and what is the relation or the contribution of statistical engineering to data science, or whether even if they are different or they are the same.
I I come back to this schematic, so I hope you can still see it. I'm viewing data science as a tool set. And some people are including statistics within data science. I think there are distinctions between them. You know, statistical engineering is doesn't advocate specific tool sets. It's advocating use the right tool for the job. So that's the reason why I emphasize as part of the tool sets not just statistics but data science, the analytics. All of that is a tool set for dealing with the data, and they take different aspects of it. But depending upon the problem, you know, the data science techniques that are distinct from traditional statistics can be extremely effective and wonderful. So this is statistical engineering is not a competitor to data science or statistics or business analytics. We view this as overarching. Now, I will admit, I believe that early in our process, Roger in particular liked to contrast statistical engineering with data science. And he's beginning to fully appreciate what we're talking about at statistical engineering is focused on the strategy and the tactics and how we can really integrate the subject matter expertise rather than on the tools. So now I know there are elements in people in data science that are interested in how to solve these complex problems, and in that sense, we feel like they're doing statistical engineering, and we're not complaining about it at all. In fact, we see them as kindred spirits. Um, what is critical here, though, is how do we solve the complex problem? And our perspective, I think, is a little broader than the perspectives that I've seen, even from the data science people who are focused on complex problems. I don't see enough of the subject matter expertise engaged. Sometimes it is. Um, so what I'm seeing is this is not competitive methods. What we're talking about is this focus on the strategy and tactics for solving these problems, which is beyond data science. It's bringing in all of these other tools. And that's where I see the distinction.
Okay, thank you. Another interesting question is that if you can say something about iterating between induction and deduction to a problem solution, and what happens if this process diverges, and if the one of the roles of statistical engineering is to make this iterative process converge.
Well, I think if I remember right, Box, in an article I invited him to write in 1999, it was statistics as a catalyst for learning. And he talked about how scientific investigations are not coherent. So I would take that in the sense that an investigative process is not necessarily going to converge, although there's a lot of experience that says, for the most part, it will, or at least give us some insights as to a better problem. And so I'm in my own thought processes, I'm less focused on induction and deduction as between the abstract and the concrete. So, in my own personal experience, we start with a concrete problem and then we abstract into the world of mathematical models that may be now, you know, millions of lines of computer code based off first principles. But nonetheless, what we're doing is we're building models that we can work with very easily, much more easily than a physical model. And we're trying to see insights as to whether or not that is going to improve the situation. We then come back to the concrete world and collect the data, and we see what the data tell us. Viewed from that perspective, and this is how I really view the scientific method, it generally is going to work. I mean, there are occasions where we don't see the solution. I got it. I've had situations like that. But at least we've done a thorough investigation of it. So the ultimate notion of the theoretical conversations about convergence through the inductive deductive method, I'm less focused on than rather than this kind of general approach for solving problems, recognizing that, hey, frankly, sometimes we don't come up with a very good solution, and I recognize that, and we move on. And we hope to learn from that failure. And often what happened in that failure is we really didn't define the problem properly.
Okay. One more question is, how do you measure or predict the sustainability of candidate solutions?
My experience, we go out and test them, and if you can develop a model that will allow you to stress test it, that's really very, very valuable. In some cases, you can't do that. In some cases, we're going to conclude that we have a sustainable solution, but we put in place, all the safeguards, all the quality management safeguards. That's fundamental to coming up with a sustainable solution. So if we're dealing with a chemical plant, we want to make sure that the recommended operating conditions are in fact robust. As a statistician, when we do response surface methodology, we like to see that optimum be very, very crisp in terms of the statistical model. All the terms are strongly statistically significant. That makes the statistician happy, but it doesn't mean you have a robust solution. In fact, you don't have a robust solution. And Box has talked about that. Normally with a chemical process, when you're in that final solution, the surface is more of a dome, which means it's relatively robust. That's important. But then you have to have the safeguards in place to make sure the process doesn't drift. Sooner or later it is going to degrade, and in some cases it degrades almost immediately, which then means I would argue that you really weren't in the final solution phase. You're still in developing the tentative solutions. So it's just a moment of when do you declare success, and the measure of success is how long is it before you have to go back and revisit that process.
Okay, thank you very much. I think that it's time to close the webinar. So thank you very much, Jeff, for your very interesting talk, and everybody for attending this webinar.
Thank you for letting me present. I've had a good time. I hope people learned something.